In this video, we are going to be talking about inverse functions, and our first objective is being able to identify a one-to-one function. A function must be one-to-one in order for it to have an inverse. And what it means for a function to be one-to-one means that if the x values are not equal, then the y values should not be equal. So just as a quick example, we talked about this in class. Think about the function x squared that sends -2 to 4 and also sends 2 to 4. That is not one-to-one because these are two different x's that go to the same y value. So that's not one-to-one. This is in fact 2-to-1 because it's sending those two different values to one y value. So we want to look at these examples here and determine if this function or if this relation is one-to-one. I'm going to draw it out in terms of columns with x's and y's. The first point, 2, 1, sends 2 to 1. 4, 2 sends 4 to 2. 7, 3 sends 7 to 3. And -2, 1 sends -2 to 1. So this is not a one-to-one function because we have 2 going to 1 and we also have -2 going to 1. Each x value only goes to one y value in example 2. And so this is a one-to-one function. So in the first two examples, we looked at relations and determined whether or not they were one-to-one. Examples 3, 4, and 5 show us how we can use the graph of a function to determine whether or not it is one-to-one. A one-to-one function will pass the horizontal line test, which means that if you were to draw a horizontal line on the graph, that horizontal line should only touch the function once. If that is the case, then the graph passes the horizontal line test, and it is a one-to-one function. If you're able to draw a horizontal line that touches the function more than once, then that means that this fails the horizontal line test, and this is not a one-to-one function. Because we have several different x values that are all being sent to the same y value. So that's not one-to-one. This last example here passes the horizontal line test. That is a one-to-one function. Examples 6 and 7 want us to use this definition to prove that a function is one-to-one. The definition says that if f of a is equal to f of b, so I'm going to assume that f of a is equal to f of b, which means that 3a plus 2 is equal to 3b plus 2, because f of a just means replace that x with a, and f of b just means replace that x with b. We should be able to show that a is equal to b, which we can quickly do. And then we're able to conclude that this is in fact a one-to-one function. And keep in mind that we knew that this would be a one-to-one function because the graph of 3x plus 2 is a line with slope 3 and a y-intercept at 0, 2, and this line definitely passes the horizontal line test. Looking at example 7, if we think about what 3x squared looks like, the graph of 3x squared is a parabola that was stretched vertically by a factor of 3, so it looks like this. For instance, I know if we plug in 1, we will get out, if we plug in 1, we will get out 3. And if we plug in -1, we will also get out 3. And I plotted those 2 points to emphasize that this graph fails the horizontal line test. So we are able to show that this function is not one-to-one by showing that f of 1 is equal to f of -1, because both of these are equal to 3, but these x values are not equal. And because this is happening, that function is not one-to-one. The next objective in this lesson is for us to be able to determine whether or not two functions are inverses. And the way that we do that is that we use composition. So we learned about composition in a previous lesson. Looks like this, which is us plugging a function into another, and we know it's always the second function being plugged into the first. So what this tells us is that if we plug f into g, and we get back out exactly what we started with. So a better way to think about this is what this is telling us is that if we plug x into g and then plug that into f, and we get back out x, and if it also works in the opposite reverse direction of composition, that if you plug x into f and then you plug that into g, you get back out x. If both of these things are true, then they are inverses of each other. Then f and g are inverses of each other. So let's look at an example of that. So in example 8, what we're going to be checking to see is if I take f composed of g of x, will I just get back out x? So this means I need to plug g into f. So I'm going to take the x that's in f and replace it with g. I'll distribute this 3. The 6's cancel and I'm only left with x. We also have to check the composition the opposite way if we were to be plugging f into g. So this means I'm going to take the x that is in g and replace that x with what f is. I'll distribute this 1/3. The 2's cancel out and I'm only left with x. So this means that f of x and g of x are inverses of each other. Now let's check example 9. I'm going to start off the same way by evaluating f composed of g of x. So I'm going to take the function g and I'm going to substitute it in for the x that is in f. So I have 5x plus 1 plus 1 over 5, which leaves me with 5x plus 2 over 5. The 5's cannot cancel out here, and more importantly, this is not equal to x. It doesn't matter, I don't even have to check the composition the second way, simply because that first one is not equal to x. I can conclude that f and g are not inverses of each other. The next thing we're going to do is we're going to use these 4 steps to find the inverse of the one-to-one functions on the next page. So here is a linear function. F of x is equal to 2 plus 1/2 x. We want to find the domain and the range of both functions, and we also want to find the equation for the inverse. I'm going to add the condition that we're also going to graph the inverse function, at least for example 10 we will. Before I start off, I want to point out that there are a few points that are on the graph of there's several points that are on the graph of the original function. For instance, I can see that 0, 2 is on this graph. I can see that -2, 1 is on that graph, and I can also see that 2, 3 is on this graph. So that means that the original function sends -2 to 1, so the inverse function I would expect to send 1 to -2. If the original function sent 0 to 2, I would expect the inverse function to send 2 to 0. And if the original function sends 2 to 3, I would expect the inverse function to send 3 to 2. So I'm expecting for the graph of the inverse function to look something like this. And now let's go find that function. So step 1 tells us to start off and replace f of x with y. Step 2 tells us to switch x and y. So when we switch x and y, our new equation becomes x is equal to 2 plus 1/2 y. Step 3 tells us to go in and solve for y. So I'm going to subtract 2 from both sides of this equation, and then I'm going to multiply both sides of the equation by 2 so that the 1/2 y will cancel out. Do make sure to use parentheses when you multiply by 2 on the left side of the equation, because you will eventually have to go and distribute that 2 to get that y is equal to 2x minus 4. And that is our inverse function, the same equation of the line that is graphed in orange there. And if you notice that these two lines have some symmetry, they do, because the graph of a function and its inverse are reflections of each other over the line y is equal to x. Last and not least, let's talk about the domain and the range for both of these functions. Let's start off with the original function for the domain of f and the range of f. F is a linear function. It has no denominators that could be ever equal to 0, and it has no even radical, so its domain's all real numbers. And because it's a line, its range is also all real numbers because it goes up and down forever. Similarly, the inverse function was also a line, and so it also has a domain of all real numbers. And because it's a line, its range is also all real numbers. The graph of f of x is given to us here. It is a rational function. Let's begin by identifying its domain and its range. The function does have a vertical asymptote, but x is equal to -1. So the domain is all real numbers except for -1. -1 is the only number that would make the denominator equal to 0. And the range of the function is all real numbers except where the function has a horizontal asymptote at y is equal to 3. So the range is all real numbers except for 3. So now that we know the domain of f and the range of f, let's go on to find f inverse. I'm going to start off by replacing f of x with y. And then I'm going to switch my x's and my y's. So all of my y's will become an x, and all of my x's will become a y. Now that I have switched x and y, my next goal is to try to solve for y. And in an effort to solve for y, I'm going to have to get rid of this fraction. So I'm going to multiply both sides of this equation by y plus 1 so that that denominator will cancel out on the right side of the equation. Do make sure to use parentheses on the left side because you will need to come and distribute the x to both the y and the 1 to be left with xy plus x on the left side of the equation. At this point, you want to get the terms that have y on the same side of the equation by themselves. So I'm choosing to move the xy term over to the right side of the equation. And now that I have the terms with y on the same side of the equation, we can factor y out. And then once y is factored out, to finish solving for y, we simply need to divide by whatever we have in the parentheses. And that gives us our answer for f inverse of x. And now that we have f inverse of x, we can talk about what the domain of the inverse function is and what the range of the inverse function is. Well, for the domain, I need to look at the denominator of the inverse function, and when we do that, we can see that we definitely need to exclude 3 from the denominator. So the domain of this function is all real numbers except for 3. For the range of this function, we need to think about where this rational function is having a horizontal asymptote. Looking at the ratio of these leading coefficients, 1 over -1 means that the HA for that rational function would happen at y is equal to -1. So its range would be all real numbers except -1, which is to be expected because the domain of the original function should be the same thing as the range of the inverse function. Similarly, the range of the original function should be the same thing as the domain of the inverse function because you get them by switching the x's and the y's. In our next example, we start off with a function that as it would be originally written, x squared plus 3 would not have an inverse because we know that the graph of x squared plus 3 is a parabola that was shifted up 3, and that graph does not pass the horizontal line test. So we add a condition on it, an inequality on it, a restriction that guarantees that the graph will pass the horizontal line test. So x greater than or equal to 0 says only look at the right half of the graph. Only look at the x values that are positive or 0, which is why we only see half of that parabola there. When we have that restriction, the graph then does pass the horizontal line test and does have an inverse. So now we can proceed with finding its inverse function. Keep in mind, though, that because we had to put that restriction on that function, we would say that the domain of this function f is 0 to infinity. It is not all real numbers, because if we put all real numbers, then the function does not pass the horizontal line test and does not have an inverse. The range of this function we can see is 3 to infinity. Smallest y value on the graph is at the point 0, 3. So to get started, I'm going to replace f of x with y, and then I'm going to switch x and y, and now I'm going to work on solving for y. So I'm going to subtract 3 from both sides, and then I'm going to take the square root of both sides of the equation, but when we take the square root, we have to think about plus or minus. Because we chose the positive x values, we choose to take the positive square root. And we're left with f inverse, once we have solved for y, is equal to the square root of x minus 3. Now we know the square root of x minus 3 is the graph of the square root of x shifted right 3. And so that function looks like this, which we can see does make sense because that is a reflection of the original graph over the line y is equal to x. Finally, let's go on to find the domain of this inverse function. It's an even radical. We find the domain by taking what's under the even radical, setting it greater than or equal to 0 to get x is greater than or equal to 0. 3 to infinity, which is the same thing we have for the range of the inverse function, and of the range for the original function. And now let's find the range of the inverse function. Looking at the graph, we can see the smallest y value on the graph of the inverse function is 0, and that graph goes up forever to infinity. The last example we have is we're given the graph of a function and we want to graph the inverse function. So the way that we do that is we observe that points on the graph, for instance, like 1, 4, to get points on the inverse graph, we simply need to flip the coordinates. So 4, 1 would be on the graph of the inverse. If the point negative 1, 2 is on the graph of the original function, then the point 2, negative 1 would be on the graph of the inverse function. And I went ahead and started connecting them. Here we have the point negative 3, 1, so I'll plot the point 1, negative 3. And then here we have the point negative 4, negative 2, so I will plot the point negative 2, negative 4. And then we have a graph of the inverse function. So to do this, all we really need to do is to switch the x and y coordinates.